So I would like to invite Jean-Pierre Raskin to come with us. He's going to make the first keynote presentation. And so Jean-Pierre is from Louvain School of Engineering in Belgium. And he's going to make a presentation entitled Information Communication Technology for the Best and the Worst. So Jean-Pierre, if you can come right here, I will put the presentation.
Thank you very much. Okay, hello everybody, good morning. Thank you for the invitation. I'm quite impressed because usually when you start talking about sustainability in the engineering field, you are in a small room with just a few attendees. You feel like be part of a secret group, a secret club, but not this morning. I'm happy to be here. I hope that you will enjoy this presentation. Okay, then before maybe starting the core of my presentation, I'd like to introduce myself. I'm a researcher working in the field of microelectronics for now more than 25 years. And I'm quite happy to lead a group of approximately 30 researchers. And this group is working, let's say, on two major topics. The first one is really the on-chip training stage for materials characterization and properties tuning. Then what we do, we use the internal stress in thin films to study the electromechanical properties of materials, or to change the properties of materials by straining the semiconductors. As you know, we can, for example, increase the carrier mobility and many other things that we can do with this technology. And this is a part of my group. And the other part of the groups is really working on high-frequency microelectronics for wireless communication, which is really the right topic here at the conference. They really work from material, and we work on new type of materials, so substrate, try to also model and characterize on-wafer devices. We try also to come up with new architecture of transistors, and we go up to a few demonstrators and we design circuits. We make, of course, characterization over a wide frequency band and a wide temperature range. And then during that conference, I have three of my researchers and colleagues. They make presentation about really VCO, LNA, and switches. Okay. I have to tell you that I'm very lucky. I'm a professor at university. I really enjoy working with all of those young scientists. But when you step back and you start thinking about really the real impact of our developed technologies, when you think really about the meaning of this research work at the university, when you have also questions that they are raised by the students that you have in the classroom, when you discuss with those researchers, young but also older researchers, and a contact also with citizens, you have some difficulties, and I still have some difficulties today to make connection between these, let's say, fantastic and very fascinating technologies. I love those technologies. Don't believe the opposite. But it's difficult to make connections with these current society challenges. And you feel really unsatisfied. And then you start thinking, you start to read a lot of things, and I started, let's say, 10 years ago to read different books, articles, outside the engineering field, hoping to come back in my discipline and do something, because anyway, this is the only discipline in which I know a few things. This is really my journey. This is really the outline of my presentation. I will start first to see what is the current innovation trend in our field, and I think that Keysight made a very good introduction to the keywords that we need to work on. I will try to show what is the connection between the ICT and the environment. I will try to show you and demonstrate that there is an urgent need to move towards more sustainable technologies. There are a few things that they have done today in industry and also in research centers and academia to really develop more sustainable processes. I will show you a few examples. I will show that we are here scientists and engineers. There are techniques, there are possibilities to design differently. Those techniques exist, those methodologies exist, and you have to use them, and of course, to realize that there are also some limits to those different methodologies. I will try to show them. And I will conclude my talk with a few takeaway messages, and one of them is really the urgent need to adopt a holistic approach. Okay, when you start thinking about what you do, and when you see all of those fundings, and I heard that, okay, if you want to get some money for making research, you have to talk about those buzzwords. We have heard about artificial intelligence, 6G. If you don't talk about those, or quantum computing, I'm part of the game. I have to do the same thing as well. But it is based really on beliefs. We have really the impression, we are convinced that, and this is about the Green Deal in Europe, that basically we have the impression that by optimizing our living ecosystem, the existing one, without changing it, we can maybe be successful. We can, and we have done to do that, digitalize the world. This is a belief. There's no scientific evidence for that. And from the other side, you have scientists, you have NGOs, you have activists, but you have also now a few small companies that they say, be careful, ICT might be a disaster. ICT, it's producing some gas emission comparable to airplane today, and maybe in the future to the traffic of the cars. And of course, one other thing also, because everybody is focusing on this climate change, and of course this is a very hot topic, very important topic, but there are other issues, for example, the end of life of all of those electronic objects. Then if you go back just to the CO2 emission, because it's a topic that you cannot avoid in all of the media, everybody is talking about this CO2 emission. It has been grown by a factor of 6 if you compare to 1950. And then what you can see here on the graph is that in the US, if you compare to 2000, which is basically the date that we can consider to the massive deployment of digital objects, US nearly unchanged compared to that date. In Europe, we show a slight decrease, but when you look at the numbers, and when you go deeply all of those reports, that it's public reports, you realize that it's mainly due to the deindustrialization of Europe. And you have, of course, the transfer of this industry from Europe to Asia, and it's the reason, of course, that the CO2 emission in Asia is starting to increase drastically. Then there is, of course, during those time, from then now more than 70 years, engineers are doing a fantastic job. They optimize all of the technologies, and not only the ICT, but all of the technologies have been optimized. Unfortunately, we see that the CO2 emission is still increasing. There is no decoupling, because some economics are still hoping to have this decoupling between the economic growth and the use of resources. But it's not happening. Of course, scientists, the industry, and the NGOs and the politicians, they are aware about now this increase of this CO2 emission, and then can have some very important impact on the Earth and also on the human being. Then the position is just to say, let's fix some objectives, and you all know this net zero emission of CO2 for 2050. That means that we have to reduce by a factor of 2 the greenhouse gases emission every 10 years. Okay, this is the objective that we fixed, for example, during the conference COP21 in Paris in 2015. But when you see that graph here, unfortunately, with all of these current policies that have been written since that date, even if you apply carefully all of those policies, you don't follow the curve of 1.5 degree. You are far, far, far from that curve. Digitalization alone will not solve the problem. This is quite clear. We have to go to a profound change of the economic model, a profound change of the resources, the way that we use them, and also the way that we share the profits. Then let's dive maybe more precisely about the different factors that can explain really the environmental impact of the ICT. I have the Moore's law. I think that all of the engineers here and scientists also in the room, we know this Moore's law. I have been working for keeping track on this Moore's law for more than 25 years without knowing that it's an economic law. Nothing that just an economic law, because people are forced to be clever, to come up with some engineering tricks to still have this downscaling of the transistor by a factor of 2 every 18 months at a fixed low production cost. And then the engineers are pretty good, pretty smart. Then you see that today, of course, we have memories with more than 500 billion transistors, or microprocessors with 50 billion transistors over a few centimeters square. This is quite amazing. But what are all the costs? Of course, we know the profit that we can take, we know the costs of the production, but what are all of the other costs? And I would like to list here a few of those other costs. One of the first obvious costs is, of course, the pressure on the materials, on the minerals that you need for building those chips. At the 80s, you see here with the Mendeleev tables, I highlighted all of the atoms that you need for producing a transistor or a circuit. And you see silicon, of course, you have oxygen, you have boron, phosphorus, aluminum was used for the connections. In the 90s, at that time I was at the engineering school, and then we started to say, okay, you know, with the downscaling of the transistor, we can see that the access resistances to the transistor increase, that we need to set aside the access, then the source, the drain, the gate, and have, you know, a mix between semiconductor and metallic. And then we use titanium, we use cobalt to reduce the access resistances of the transistor. In 2000, we have a very breakthrough in terms of usage of materials. Why? Because you don't scale, of course, the transistor, but you don't scale the transistor only in the plane. You have also to downscale and to reduce the thickness of the dielectric stack, which control the channel of your transistor. As you know, today, the thickness of the gate oxide is approximately 1 nanometers of silicon dioxide, equivalent silicon dioxide. It means 3 atomic layers. If you have just 3 atomic layers as a dielectric, due to this quantum effect, which is called the tunneling effect, you will have this huge leakage current through the gate. Then, engineers said, no problem, we are going to thicken this dielectric, use a high permittivity to still have a good electrostatic control of the channel, and then we had to introduce most of the materials that you see here in orange, like, for example, the hafnium dioxide. Okay? Then you have to have this pressure on the material. But what does it mean to have all of those materials now in the chip? Just here on this graph is just to show you the abundance of those materials in the Earth crust. This is, of course, an average value. And then, of course, just keep in mind that the scale here, it's in log scale. You have 10 decades of difference between the most abundant and the sparse. If you take, for example, here iron, you have to extract 1 ton of ore to have access to 330 kilograms of iron. But if you go here to the bottom, if you want to extract platinum, and you know that platinum is a very popular material that we use in microelectronics or for electrochemistry, and you see for platinum, you extract 1 ton of ore, but you can just retrieve from that ore 3 grams. 3 grams compared to 330 kilograms if you just focus on iron. In the 1950s, the material that were used for producing product and services, they are highlighted here on the graph. You see a limited number, and of course, because the engineers said these are cheaper, they are more easier to access to. But now, because of the complexity of the functionalities, we basically use all of the materials. But what does it mean? It means that, of course, because you have to extract materials like gold or titanium, platinum, that have a lot of what we call the gray energy, that the energy that you need to extract those materials. You have more and more materials with a lot of gray energy. It means that it translates also to more and more gas emissions. This is the first thing. And diversity of material that I use are increasing. Second factor is the increase of the process complexity. You see here on the graph, let's take a pointer maybe. See on the graph here, this is the number of process steps for the fabrication of your integrated circuits. And depending, of course, of the node, you see this is shortened nodes here, you have an increase of the fabrication steps. Today we are with approximately 1,300 steps to build up a complete circuit. At the same time, you see that microelectronic industry, it's really very wealthy. You can see this is an increase over the year, starting here at the end of 70s, of 9% per year. And of course, if you combine these, let's say, the complexity of the fabrication and the number of sold ICs, you have here an increase by 16% of the energy footprint of that industry, knowing that we have to reduce the CO2 emission, and this is for all of the different companies. And it's really a challenge for the microelectronics industry. Third factor, it's a new market. This huge economic growth expected, and as mentioned and highlighted by Keysight just before my talk. We expect to have a huge increase of this use of those new technologies for Internet of Things, for artificial intelligence and 6G. We talk about $1 trillion market by 2030. And of course, these will have a huge impact also on the environment. Fourth factors, and it has been also mentioned just before my talk, this is the CHIPS Act. This is really an economic war where you have all of those different continents that they would like to have their own fabs, they want to have their own productions, their own IPs. And then there is an increase those last 15 years by a factor of 3. Can you imagine? 3 more clean rooms facilities over the world those last 15 years. And of course, you can see that most of them are now in Asia, and of course, Europe and the US would like to also increase that number in the continent. Okay. Everything has been based up to now on just one unique factor, which is this gas emission. Everything is about climate change in the media. But unfortunately, it's more complex than that. You see here on this graph, the scientist has demonstrated the coupling between the way of living and the health of the planet. And you see that the climate change is right here. And then we cross the planetary limits for this climate change, then the concentration of CO2 in atmospheres. But unfortunately, we have also transgressed other limits, like, for example, the land pollution or the fresh water pollution. They are also in a bad situation. And as an engineers, there are also other factors than the CO2 emissions that we have to take into account. And basically, I don't have time, but they are, again, the methodologies are there. The possibilities to make calculation, evaluation of different indicators. There's 16 different impact indicators. They are available in literature. And there is, of course, an urgent need to move to a more responsible innovation. But now, people are doing things, and not just in the academia, also in research centers and companies. They are trying to do their best, okay? And then this is what I would like to highlight here. the ongoing actions to reduce the footprint of ICT. Just here on this graph, this is really based on the public report of those companies. You see EuMC, TSMC in Taiwan, and ST Microelectronics in France. And I may see here just 2 indicators. Again, as I told you, there are 16 indicators. I've just taken here 2 of those. The first one here is the primary energy demand, which is the use of energy for running the factory. And the other one here is the water consumed. And then what we can observe, for example, if we just look at ST Microelectronics, we have a slight decrease of the electric energy use and an increase of the renewable energy. In terms of water, we see also that it's slightly reducing or pretty constant over that 10 years. You see from 2010 to 2020. Unfortunately for TSMC, running for always shorter and shorter technologies, they have a very hard time to reduce the energy use and the water use. You see, this is very important increase. Okay, then when you say, okay, ST or EuMC, they are doing pretty good. Yes, it's true, they are doing their best. And then they can reduce the consumption of energy and water. But just please look at the unit. This is per centimeter square, okay? And now if you produce more, and it's the case, if you take the same period of time, these 10 years, they have increased the production by 70%. Then the engineers, again, the engineers are doing a very good job. They reduce the use of energy and water, but at the same time, if you produce more, if you sell more chips, the absolute increase of those, the use of those resources is there. Now, another program also in the industry is try to recover and recycle all of the metal during the process. And it's true that, I don't know if some of you here in the room are working on processing, but we all know that when we make deposition of metal, could be by evaporation, sputtering, most of the metal will be deposited over the walls of the chamber. On top of that, it could be more than 80%. And the yield is pretty low. And moreover, the target here, this is the target, the substrate, and here is the crucible where you have the material that you like to sputter or to evaporate. The target is never completely consumed, okay? Then you have also this remaining material in the crucible that usually it's not used anymore. Then there are a lot of material that then can be recovered in the company, and there are several programs that they try really to recover those materials. But we are talking really about, 90% of the material that can be really retrieved if we do it properly. But again, for the first example, when you say to the industry, you are going to reduce your energy bill, reduce the water bill, reduce the material bill, they say, yes, please come and work with me. Because, of course, this is good for the environment, but this is also good for the economic profit. Now, there are also several actions in the academia and also in the industry to come up with new chemistry. But this is now today still at the research and development stage. For stripping, for wet etching, for cleaning, for decontamination, there are a lot of different possibilities to reduce the toxicity of the materials that we use. And also for lithography, there are now more bio-source water soluble resist to avoid the use of solvent and alkali-based developers. Again, this is really at the research phase. And the main motivation for the industry, they know that new legislations are coming. They would like to be prepared for those new upcoming legislation. That legislation, of course, it's the economic the economy, it's a leveler, and also the legislation. In Europe, we have now a pretty big project, which is called Genesis, where you have 60 partners all over Europe from 12 countries. And they decided really to work together because they are really convinced that sustainable semiconductor industry must be the concern of everyone. It cannot be the source of competition. And of course, the collaboration will be key. And it's just a starting project, and we'll have to see how people are going to exchange, share information to hopefully reduce the footprint of that big industry. You see the objectives are quite ambitious. Try to reduce by 50% the hazardous materials. Try to reduce by 30% the emissions of gas and the production of waste, and improve the recycling of the rare materials. I was talking about, because we are engineers, we are scientists, we need methodologies. We need methods to evaluate, to calculate, to compare, to improve, to optimize, and hopefully to eco-innovate. And as I told you, those techniques exist, and they are even standards. You have the ISO 14040, then this is what we call a life cycle assessment. And the life cycle assessment really help you to calculate, to evaluate the potential impact on the planet ecosystems and on human health, really of any product or service, from the raw materials acquisition through production, the use phase, until the end of life of this product or service. And you see, you have this description here of from the raw material extraction up to the end of life. And then it helps you to really realize the different inputs that you need to accomplish that stage, and the waste that you have. And you can then calculate all of those flux to come up with the footprint, basically, of your product or service. And some keywords that you will see quite often in literature, it's what we call cradle. Cradle, it's when you make this LCA analysis, starting from the raw material extraction. The gate, it's when you stop the, let's say, the calculation at the at the gate, let's say, the end of the manufacturing in the foundries. And grave, it's when you also consider the end of life of the product. And of course, there is a trend now to really also evaluate the possibility to go to a circular economy. And if you take just a little bit deeper this methodology, there are 4 steps. The first step is really to define the goal and the scope definition. And let's, for example, take this example where you want to calculate one indicator, which is the CO2 emission, for comparing different MEMS release techniques. Step 2, you go to the inventory analysis. It means that I have to calculate the quantity of energy, electricity, gas, chemicals, water use for doing this process. The third step is to evaluate the gas emission, because this is really the indicator that I would like to calculate, which is associated to those used resources. And of course, based on all of the results that you will have, you make interpretation and analysis of the results. And then you can see in literature, people are talking about different scope 1, 2, and 3. This is quite important because this fix is defined with the boundary of your study. And what we call the scope 1 is what you made this LCA, but only in the company. It's everything really happening basically in the factory. This is what we call the direct, let's say, impact, the scope 1. But to be complete, and now European legislation are going to force company not only to evaluate and to report the scope 1, but also scope 2 and scope 3. And what we call scope 2 and scope 3 is basically everything that the company needs for the production. It means needs energy, then you have to take into account, of course, the the resources that are needed to produce that energy, you have to also consider the energy and the resources used by all of the suppliers for the upstream activities, and also everything will be after, let's say, the production of the product will be on the market, then you have to consider use phase and the end of life, the transport of those services or products, and this is what we call the downstream activities. This is for scope 3. You see? But a lot of things to consider, which is really outside your main activity. Then you need, again, cooperation is the key word. Okay, in my group, we have been using those, let's say, well-established methodology to make several comparisons. I'll just take here a few examples. For example, if you have to make some power electronics, RF power electronics, you have different technologies, different possibilities, and how to choose. Today, basically, we have several factors, but usually it's the performance, it's the area, it's the cost of the technology, the power consumed. But here you can add up other indicators, and for example here I put the global warming potential, this is the CO2 equivalent, and the abiotic depletion potential, just two more indicators. And then what we could observe that, of course, depending on the type of substrate, this is a log scale, you see from silicon to fully depleted SOI, trap-rich SOI, GaN silicon up to GaN silicon carbide. Now you see that there is a huge difference between these when we see those environmental impact compared gallium on SiC or gallium on silicon, and of course even more impacting if you just go to SOI. Then this is basically when we saw the table from Keysight where we saw different features, it would be great also to add up in those table other indicators to make really fair comparison between different technologies. We made also MEMS devices, different sensors in the group, and then when you start also comparing not just the performance, not just the reliability of the sensor, but also the environmental footprint of the sensor, you can do it because the tools again are there. You make the calculation and you observe that basically if you want to define this membrane, this is a pressure sensor, make comparison between wet etching and here dry etching. And then a huge difference in terms of CO2 emission. The wet etching is really less impacting. Then you can make a choice knowing exactly what you do. Last example here, this is the spiking neurons for neuromorphic system. This is also a quite popular topic in which you can see a lot of people using those phase change materials. In our group, we work on the vanadium dioxide, and all the publications that you can see, they use gold contact. If you use gold, it's a disaster. Of course, it's great gold because it's quite stable, it's quite reliable. Then we decided to make some reliability study of those spiking neurons by replacing gold by aluminum. Of course, you reduce by a factor of 10, even more than that, the impact footprint. And based on our studies up to now, we see that we don't have any differences in terms of performance for this example, which is not always the case. Okay, you have to pay somewhere also your choices. Another example, it's if you're interested by the topics of sustainability, you will see that scientists and a lot of papers and literature are really talking about the extraction of materials. They are talking about reducing the use of resources in the manufacturing stage, but they don't talk at all about the end of life. This is really incredible. They don't talk about the end of life of all of those objects. And then if you see electronics today, it's 70%. They just go to landfill. When you hear at the radio, I don't know here in France, but in Belgium, we hear all the time, please bring back your electronic object. We will give them a second life. This is not true, okay? Of course, it's better to put them in the container where people, they will try to do their best to treat them. But at the end of the day, 70% again, they go to the landfill. only 10 to 15% I treated properly, and one of the, let's say, most advanced company in that field is EuMC in Belgium. They crush, they shred really the electronics devices to recover just a few materials. Technically, they told me that there are approximately 70 different materials. You remember the Mendeleev table? We have approximately 70 different atoms. They can technically extract 17, okay, out of that. 17 out of 60 or 70. But they just extract 4 or 5 because they are the only one they are really economically profitable. And the ones are gold, silver, platinum, palladium, and copper. That's it. The other, they don't try even to get them because they are not profitable. Because, of course, just the raw materials are still too cheap that you can extract from most of the time the southern countries. Oops. Then there is a clear need to really think about more circularity, and of course, you see here on the graph, if you keep the loop short, it will be better. And of course, the most interesting things to do with all of those electronic objects is to extend their lifetime. This is something that we have to think when we start designing those objects. If we don't think about the end of life, it's difficult afterwards to extend the lifetime of those because they cannot be repaired. They cannot be really reused or repurposed. And this is something that in terms of design and engineers, we have to think ahead. Another example, this is a PhD student, started his work in my group now 1 year ago. It's really try to say, okay, it's a pity that we see all of those electronic objects, like here, for example, a smartphone, and at the end of his life, as I told you, the best, we are going to shred this electronic components and try to retrieve a few materials. And then the recycling is not really the best way for the microelectronics. The best is try to keep the function running. And believe me, we signed here a contract with Fairphone. Fairphone, it's a Dutch company, trying to develop some what we call modular smartphone, that they are easy to upgrade, to repair, and so on and so on. Then it's pretty easy to dismantle this smartphone, and we started with that one. We start now also a contract with Samsung, where we try to basically analyze, measure the quality of those electronic functions, then keep alive the functions. Don't try to retrieve just or to recover the materials. Then we have received the 3,000 smartphones that they cannot be refurbished as a smartphone, but basically all of those components, when you take them isolated, they can still be used for other applications, other functionalities. And we have projects now using in IoT, using those, let's say, second-hand electronics, after, of course, certification and so on and so on. This is not easy, okay? This is not easy, but this is doable. Okay, now to go to the conclusions, we can raise the question, I talk about these methodologies, are LCA sufficient for providing guidelines towards sustainability? When we think about the global impact of ICT, as I told you, we are working, all of us here, on a technology. And then we can at least use this life cycle assessment technique to evaluate. This is the minimum that we should do. It's to analyze the direct impact of what we produce. Is it sufficient? No. To my point of view, it's not sufficient at all. Because, of course, as you know, when you have made those objects, they will be on the market. They will induce some effects, some different habits. And we will have also the obsolescence effect. It's what we call destructive innovation. Then the application will induce some changes that we cannot maybe even think about. And then, of course, even deeper, more systemic effect, you will change the behavior and the structure of the society. And this is what we can see with this very symbolic example of the smartphone. As an engineer, we are not prepared for that. We don't have the knowledge for that. And we have to work with different people, different scientists coming from humanities, for example, science. Yes, we'll have to work with sociologists, with anthropologists, with economists, that they are ready also to work with engineers to think differently. And there's a fantastic book that I read now maybe 8 years ago, written by Professor Ashby, maybe Mike Ashby, maybe some of you here in the room knows him. It's a professor in Cambridge University. He's mostly working in material science. It's a fun, to my point of view. I'm an engineer. I have to think, step by step. We have to take, have to give some, concrete methodologies. And this book really provides me what I was looking for. I don't have time to explain, but please, if you want to discuss about this methodology afterwards, this is what I'm trying to apply now for all of the, let's say, engineering students that they make a master thesis or a PhD thesis with me. We try to apply this methodology to basically be more conscious, be aware about all of the stakeholders when you develop a technique, to be aware about all of the impacts. Not just look for performance and cost, but also the other indicators, as I mentioned before. Try also to realize, and this is the table here, for example, the impact of what you do on either the people, the social impact, ecological impact on the planet, and the economic impact, of course. And then if you make that exercise on any developed technology, you will end up with a similar table where you see red and green. Red, it's not good. Green, fantastic. It's positive for the planet, it's positive for people. Any technology, you will end up exactly with the same table. That it means that you have, at the end of the development of a technology, you have to discuss, you have to debate, you have to realize what you do, you have to raise your consciousness. And this is the minimum, again, that we can do, even if it's not going to change the face of the world. This is what we have to do as a scientist, to my point of view. Okay, conclusions. I hope that you understood that LCA are there, those methodology. They are there that you can help you for thinking about the development of any technologies or services at the early stage of development of this technology. Is it easy? No, it's very difficult. It's pretty complex because you need to access to a lot of data. The data doesn't exist most of the time. You don't know exactly the electricity used by this piece of equipment. You don't know the gas that they are ejected because there are no sensors today. There are companies that they're imposed to the providers of those equipment to have those kind of sensors, to have at least a monitoring of all of those flux. Of course, there are some IP issues. No, it's not easy at all. But okay, as I told you, there are some initiatives where people they are really, ready to work together to come up with correct data. As I said, LCA is not sufficient. It's just the beginning of the story. It's a starting point. This is something at least you can go to the table and discuss with economists, sociologists. You can come with numbers. You can come with indicators, which is not only the frequency of the clock of the microprocessor or the power of your power amplifiers or whatever. You can come with other arguments, other elements to discuss about your technology with people that they have other knowledge in economy or social sciences. In our technical liberal society, I think that we are encouraged to develop what philosophers call creative destruction. Try really to come up with new ideas that's going to make obsolete the other ones. And we have to really to change our mindset to go to appropriate and appropriable technologies. You can just come back to one of the first slides where I say that Moore's law, it's an economic law where basically we try to produce those tiny transistors at a fixed low production cost. We could maybe one day, and just imagine if you change just this driver, change the rules, just change, because we are just, you know, very good technicians, well-paid, very well-paid technicians, the engineers and the scientists, to, let's say, answer to some questions that are raised. And if we just change our mindset and this utopian law that is going to be, for example, the number of transistors must double approximately every 18 months, but with a fixed environmental impact. I don't know what would be the results, the keywords, the buzzwords that would be used to describe that, but today for sure has been demonstrated during, of course, the conference. This is still power, performance, cost, and area. And this is the PP, the famous PPAC figure of merit. Then certainly tomorrow we will be forced, I suppose, but this is my belief, and you can disagree totally with me, that tomorrow we will have other drivers that we have to take into account, which is going to be basically the environmental impact, but also, and insist, also the social impact, which is even maybe more important, and we will have to face that maybe even earlier than what we call the climate change. Thank you for your attention.
Thank you very much, Jean-Pierre. Do we have questions from the audience?
Thank you for the amazing presentation. I think it's really an eye-opener. As a microwave engineer, I feel a bit concerned. However, I have a remark regarding basically, I see a lot of hardware. But my comment is that quite often we have to dump the hardware because of the software. And if you go to a software engineer, will tell you change the hardware. That's the solution. I think there is a need for optimization at all stages, because I mean, you dump your mobile phone simply because you cannot update anymore. Just throw it away. It's still working very fine, but you have no choice.
I fully agree. When I say systemic approach, of course, the examples that I've shown here is just because I'm really working on the physics of semiconductors that I cannot talk about software. I'm not pertinent in that field, but I have colleagues that, of course, they work in that field and try to have more efficient, because most of the time people are working in the software industry, they know that the hardware will be there. Then they don't really, you know, take really care about the efficiency of the design of the software. And I fully agree. And again, this is communities that they work not together. Then it's one of the key words. Please try to work with other colleagues that they would like also to change things. And for sure, we can do a lot, if we can really have more collaboration between software and hardware engineers. I was talking about sociologists and so on. I agree. This is the next step. First, we have to work between engineers much more. And we know we are part of big institutions, the same at the academia. I see that even people working in antenna, they don't work, and I have to blame myself, okay? I'm not saying that I'm doing. That's nice collaboration. But people on antenna, other RF designers, they don't talk each other, and so on and so on. And there are a lot of things just by sticking on engineering field, and you point out here a very good point, of course, the software optimization to reduce the pressure on the hardware. Yes, of course.
Okay, so if there are no other questions, we have to move forward. I really invite you to join the session on sustainability. Actually, Jean-Pierre will be one of the chair, and also the CHIP Act Inter-Society panel. Jean-Pierre will be there also. So thank you again, Jean-Pierre. And we have a gift for you.